Here are a couple more examples of solving by substitution, and I wanted to point out these cases. You could get no solutions, you could get infinite solutions. Whenever you're solving a 2x2 linear system, the three options are you either get one solution, no solutions, or infinite solutions. So let's take a look at these two cases here, starting with my first example. Let's see, step number one, I'm going to go using the general procedures outlined in our introductory video. Again, this is a nice system to solve using elimination, but we'll go ahead and run through the substitution steps. Choose an equation and choose a variable to solve for. So I'm going to choose the first equation because there is no coefficient in front of x, okay? Or that is 1 is a coefficient in front of x. So it's just going to make one less step in finding x. Add 5y to both sides. And x is equal to 10 plus 5y. There's step number one. Step number two, plug this into the other equation. So I'm looking at -2 times what we just found for x plus 10y equals -6. And from here, distribute, combine, and solve. This gives me -20, minus 10y plus 10y equals -6. Well, -10y plus 10y is 0, so the y variable simply disappears, and we end up with -20 is equal to -6. Well, that's obviously not true. -20 is not equal to -6. This is a false statement. And whenever you come across this, what this tells you is that there are no solutions to the system. No solutions. And what that simply means is that there are no values for x and y that satisfy one equation that will satisfy the other equation. So, for example, let's just say y is 0 and x is 10. That satisfies this first equation. 10, a 0 here makes that go away, 10 equals 10, that works. But if I try 10 and 0 in the next equation, 0 makes this go away, but -2 times 10 is certainly not -6. So there are no values that will work for one equation and the other at the same time. Therefore, the system has no solutions. That's the no solution case. Let's take a look at this other system of equations to see what happens. Step number one, choose an equation and choose a variable to solve for. Well, that's already done, okay? I've got y equals 2 minus 2/3 x. I can use that. So actually, I'm just going to move on to step number two. Step number one is done. Step number two tells me plug this in to the other equation. So I'm looking at 2 times x plus 3 times all this stuff here. 2 minus 2/3 x is equal to 6. And then distribute, combine, and solve from there. So I'm going to distribute the 3, and that gives me 2x plus 6 minus 2x equals 6. How did I get that minus 2x? 3 times 2/3, the 3's cancel, and I'm just left with the 2. So review that fraction multiplication by a whole number. It'll really help you out. Notice what we have here when we combine the like terms. 2x minus 2x, the x variable goes away, but we end up with 6 equals 6. Well, yes, 6 does equal 6. That is true. Okay, we have a true statement. Whenever you have the true statement like this, assuming that you've done the other steps properly, then what that tells you is that you have infinite solutions. Infinite solutions. Now, in the infinite solution case, this is not the answer, although it's true. The reason why infinite solutions by itself is not an answer is because there are also an infinite number of things that are not solutions. So we have to constrain our solutions to one of these equations. So for example, we can say we have infinite solutions, and we're going to do that in set notation like this. The set of all x, y values such that one of these equations is true. 2x plus 3y equals 6. And end our set notation. This is the answer. It describes that we do have infinite solutions in that any xy point or any ordered pair of values xy that work for this equation constitutes a solution to the system. And we don't even have to put this equation. We could have put the other equation, because whatever works for this works for the other one. So let's just test that real quick. What if we chose 0 for x? That means that y has to be 2. That's a solution to this equation, 0, 2. If I put 0 here for x, then you can see that y is equal to 2 in the second equation. It's true for both equations. And indeed, anything that you can find for x and y that's true for this equation will also be true for that equation, and therefore true for the system. So here's how we answer in the infinite case. Make sure you always take it down to this level. Infinite solutions is true, but the answer is this set notation, infinite solutions constrained by one of those equations.